So this is really the easiest to predict, because when you're doing decomposition, we go from a compound, and then we end up with our products are just an element and an element. There are more complicated decomposition, but we won't be predicting the products for them, okay? So the only things you have to watch out for is the diatomic elements. Anyone forget how to find the diatomics? No, we're good, excellent. And then there's the two new ones. You need to know P4 and S8. Okay? Shh, John, shut up. And Addie too, I suppose. John, shut up. Now, all you have to do for this is you have to split it apart into its two elements. So we have N and we have F. And so that's going to split apart into nitrogen and fluorine. So is that good the way it is? Or should I put NF3? Would that be better? She's got this look on her face. I'm glad you have that look on your face because that looks terrible. What's terrible about this? Nitrogen is diatomic and fluorine is diatomic. Okay, so we're going to have that. And then at this point, we now balance it by putting a 2 here and a 3 here. And I think that takes care of it. Yes. 5, 6. So you guys are going to do the rest of these. I'll give you, I don't know, 5 minutes or so to just go through these. Probably won't even take you 5 minutes. And then we're going to move on to synthesis. So we are moving on to page 58, 5-8. And if you have problems with this and you want to watch a little video on it, there is a video, but you don't have to if you don't want to. Okay, so in this case, synthesis, it's almost as easy as decomposition. The only thing is now we aren't taking apart a compound, we are forming a compound out of two elements. So the thing about the compound is that you need to write the correct formula. Okay, so here's some things that people might do incorrectly. Okay, things you need to do, you need to make sure your cation goes first. What kind of elements form cations? Metals and H. Okay, the charges in the compound must balance. So here's ways you could go wrong. You could say, what if I had AlCl3? I'll go up here. Cl2. Do I have this down below? No, I don't. That's okay. Cl2 plus Al. This is what many grade 10s will do when they first see these. Cl2 Al. Do we like that as an answer? No. What's wrong with it? What is wrong with that? Chlorine is first. Chlorine has to go second because the metal has to go first. So let's cross that out. And now we'll have AlCl2. Do we like that one? No. Why not? Why don't we like AlCl2? The charge of aluminum is 3+, and the charge of chloride is -1. So in order to write the correct formula, it has to be AlCl3. And finally, we are correct. Yes? So after that, now you can balance it. So don't be like, oh, but I've got 2 Cls on one side and 3 Cls on the other. Well, why did we learn how to balance equations if we weren't going to do that, right? So now what we can do is we can now balance. And we can say, I need to have 2 Cl3s and 3 Cl2s. Now I have 6 chlorine, and that means I need 2 aluminum, and I'm good. Okay? So I would advise that at this time, don't use your periodic table if you have charges on it, or get rid of your charges. Try and do it without. Try to get those charges in your head. Okay, this is good practice time, right? So if you've got your periodic table and up at the top, let's say you've written +1, +2, +3, now would be a really good time to get rid of those and try it without. Okay? And if you have trouble, then you can go back to, figuring it out. So take a few moments. And you're going to work through pages 58, and then you can try on 59. And on page 59, you can try and include the phases. Okay? I think, there we are, now we're recording again. So this is 6.3D, but we're actually going to skip page 61 because I want to redo this. We're just going to start with page 62. Okay?
62?
62.
Great. That's great.
So single replacement, you have to keep in mind that if your lone element is a metal, that it will replace the metal. Okay? And if your lone element is the non-metal, it will replace the non-metal. Unless, of course, you have hydrogen. Hydrogen will also replace a metal. Basically, it's cation replacing cation. Yes? Anion replacing anion. Now, we're going to ignore the activity chart for now because we don't use the activity chart until we get to part D of the exercises. So that's why I said we're going to skip the first page because it has to do with the activity table. When you are writing the products, just like for decomposition, you need to make sure if you have a diatomic element, you write it as 2. If you have P, it's P4. If you have S, it's S8. All your other elements will have no subscripts. So just like iron, copper, sodium, like just nothing. Okay? Make sure that your formulas of your ionic compounds have the charges balanced. So if you've got a 2+ and a 3-, you're going to have like A3B2. Okay? The metal has to go first in the ionic compound. And make sure that you do not put 2 metals together. No. Okay, so let's see all the ways you could go wrong. So here's our practice equation. Here we have Cl2 plus NaBr. Let's start by having the Cl2 kick out the Na. So we would end up with Cl2Br plus Na. So many things wrong with that. What's the first thing that's wrong with that?
Not balanced.
It's not balanced, but I don't care about balancing, really. I got 2 nonmetals together. That's a no-no. Okay? So that's wrong. Plus, I just randomly threw this 2 in here because there was a 2 there. You cannot do that. The subscripts don't transfer across the arrow. Okay? I can't do it without the subscript either. That's also no good. I cannot have two nonmetals together. Now, what if I take Cl2 and now I kick out the Br and I get NaCl2 plus Br. Are we good now? Is NaCl2 plus Br good? What's wrong with it? Br is diatomic. Yes. Anything else? Have you ever heard of NaCl2? No, because Na is +1 and Cl is -1. So the correct formula is NaCl. And I don't care that there's a 2 over here. We've been learning to balance equations because we will take care of that by balancing, not by just writing random subscripts for no reason. Okay, so 2 of those, and we're done. Is good? Okay, so this will take you all the way through part A. Okay. You're going to assume that all your multivalent metals have a charge of +2. And we're just going to also very quickly take a look at part B. Okay, that's on page 64. When you get in an equation and the compound is H2O, do not leave it as H2O. It's going to make it difficult in a single replacement. You're going to rewrite H2O as HOH. Because then what you can do is you can say, okay, I have K plus, instead of H2O, I'm going to write, like, and then if I do that, then I end up with K2O plus H2, and that is not what happens. That's not what you get. Okay? O2 is it's very unstable in water, and it will rip a bunch of hydrogens off the water. So we don't want that. So we're not going to do that. We're going to instead write it as K plus H, OH, and then the K is going to kick the H out. So we will end up with KOH plus, and then we'll have H2. Which means now we have 2 hydrogens, so we need 2 hydrogens. We've got 2 hydroxides, so we need 2 hydroxides, and that'll give us 2 potassiums. Okay, so you can do parts A and B, which is pages 63 and the top of page 64. Okay, so page 63, top of page 64, and then we'll talk about the activity series.
Okay, so wait, type? Oh, it's like a single replacement.
Single replacement metal, single replacement non-metal.
That's what it means by type.
Yeah, yeah.
Zinc. Zinc.
$61. Okay. Now, page 61, elements. Just because you put an element with a compound does not guarantee that you will get a reaction. Sometimes when you put an element with a compound, they will just sit there and do nothing. Okay? So what we have to do is we have to decide, in order for a single replacement reaction to occur, the lone element, that's the one doing the replacing, it has to be more active. Okay, so our lone element has to be more active than the element it is replacing in the compound. So how are we going to tell? Well, actually, just before we go there. So if you put a more active lone element, it will replace a less active element in the compound. A less active lone element will not replace a more active element in a compound. Now, just in case you're wondering what this RXN is, RXN stands for reaction. Okay? And if no reaction occurs, you don't have to write any products. You can simply write either no reaction, or even more simply, you can just write NR. Okay? So let's take a look at our activity series. And the activity series will be available to you both in this section, but when you get to like where you have all the different types mixed up, it is also available in your data pages on page 6, 5. No. There we go. Page 5 of your data booklet has the activity series in it. Okay, so in your pink sheets, page 5, this is available. But for now, it's given to you in this sheet, so you don't need it. All right, let's take a look at this table. The most active things are at the top. On the left-hand side, we have the metals. And on the right-hand side, we have the non-metals, but the most active are still at the top. So things that are higher up can replace things that are lower down, but not vice versa. So if we have K and aluminum, K can replace aluminum. So K could kick aluminum out of a compound. Could aluminum kick K out of a compound? No. Okay? Al cannot replace K. Okay? So that's the only little added thing when you get to part C and D. You have to decide, before you get too excited about writing the products, you have to say, can a reaction actually occur if I have a lower one trying to replace a higher one? Like if I had I2 trying to replace Cl, then I would just write no reaction. Okay? So that's the only thing that's different about part C and D. So you guys can just keep working on parts A and B if you want to, or you can move on to C and D. I would recommend, though, definitely do some of part B, because it does have that water, and you need to rewrite it as HOH to do the replacement tidally. Okay? All right, my friends, I hate to do this to you because I feel like you could use more time on single replacement, but we got through this on block 2, so we're going to get through it with you guys as well. This is on page 67. 67. 67. Well, now, do you remember the term precipitate? Oh. What is a precipitate? Whoops, I got excited. I was doing the T. Anyone remember? Solid. It's a solid that forms when? Yeah? Solutions. So what's going to happen is we are going to do a double replacement reaction. Okay? And when you have a double replacement reaction, you take the cations from two ionic compounds and you swap them. Yes? That's what a double replacement reaction is. Now, what we're going to be figuring out is when we swap them and they get their new partner, is the new partner going to stay in solution or is it going to form a precipitate? Okay? And this is also abbreviated PPT. That is a standard abbreviation for that. We are on page 67. Now, this table is also in your data booklet. You will be able to use it during any quizzes or tests. Okay? Now, let's take a look at what information this gives us. It tells us that if we have any of the alkali ions, so anything from column 1, if we put that together with any negative ion at all negative ions, those will be soluble. What does it mean to be solvable? Soluble, sorry. Solvable. Able to dissolve. And if it is able to dissolve, what state would it be? Aqueous. Okay? So that means if I give you sodium phosphate, it will be aqueous. If I give you rubidium acetate, it will be aqueous. If I give you cesium permanganate, it will be aqueous. Okay? It doesn't matter what you pair it up with. All the alkali salts will be aqueous. All of them. Same thing with hydrogen, but hydrogen's a little weird. I'm going to put it in brackets because these are acids and they're a little bit different, but for grade 11, it's probably okay to just say they're all H is soluble with everything. Okay? Ammonium, NH4, also soluble with everything. So, ammonium phosphate, ammonium oxalate, ammonia bicarbonate. They're all soluble because it's paired up with ammonium. Did I say ammonia? I meant to say ammonium. Okay? So no matter what you put it with, ammonium salts are all going to be aqueous. So that takes care of our completely soluble cations. Yes? So we have 3 groups. We have the alkali, we have hydrogen, we have ammonium. Now we get to our completely soluble anions, which are acetate and nitrate. So it doesn't matter what you put with them. You can have lead acetate. You can have barium acetate, iron acetate. Doesn't matter. It will be soluble. And if it is soluble, what state is it? Aqueous. Nitrates, also always soluble. Copper, 1 nitrate, soluble. Copper, 2 nitrate, soluble. Manganese, 3 nitrate, soluble. Yes? Okay. So now we have hit all of the always soluble ones. Okay, so all of these up here, these are always soluble. Now we get into the category that I call mostly soluble. Okay, and that's going to be these 2 here. And the reason I call them mostly soluble is if you look, we have 5 different things. We have silver, lead, copper 1, mercury 1, and mercury 2. Those are low solubility, but there's only 5 of them. Yes? So if you put chloride or bromide or iodide with silver, lead, copper 1, mercury 1, and mercury 2, guess what? It's low solubility. If it is low solubility, what state will it be?
Solid.
It'll be a solid. So that would be like the calcium hydroxide we had that we were trying to make the solution from, right? In order to get anything to dissolve, we had to heat it, we had to stir it, right? It was low solubility. A little bit will dissolve, but not very much, okay? And barely anything if you just do it at room temperature, okay? Everything else belongs in the category all others. So if it's not silver, lead, copper 1, mercury 2, mercury 1, then it is soluble. It is aqueous. Now, one thing I'd like you to take into account here is this guy right here. This is Cu plus 1, not Cu 2 plus. Yeah? It's just Cu1, not copper 2 plus. Where would copper 2 plus go?
Soluble.
Soluble. Cu2 plus is in all others. Yes? Okay. So if I give you copper 1 chloride, copper 1 chloride would be solid. Copper 2 chloride would be aqueous. Okay? Same thing with iodide or bromide. Sulfate, also mostly soluble. Most things are soluble. Only these 5, silver, calcium, strontium, barium, lead, are going to be solids. Okay? That's why I classify it as mostly soluble. Then we get into the category of somewhat soluble. Okay, sulfide, it's only got 5 things other than H, NH4, and the alkalis, which are soluble with everything. Other than the cations that are soluble with everything, there's only 5 extras that sulfide is soluble with. Yeah? So if you have any of the alkalis, ammonium or hydrogen, the only 5 extra, beryllium, magnesium, calcium, strontium, barium, are soluble. Is good? Okay. Hydroxide, mostly not soluble. Okay, so that category is these guys down here, because hydroxide is really only the alkalis, ammonium, hydrogen, and then 1 extra strontium. And when you get to phosphate, carbonate, and sulfite, we get rid of the strontium and we only have these. Most hydroxides are low solubility. So if I give you iron hydroxide, right, in here, that's basically everything. Iron, copper, 1 copper, 2 manganese, 3 calcium, everything, almost. Yes? Because there's only those very few that aren't. Again, all others, this is almost everything. So does that table make sense? So what you're going to do with this one is that you are going to then predict the state of each of these salts. So what you're going to do is you're going to say, I have barium sulfate. Normally we will go looking for the anion unless it's one of the always soluble cations. Okay, so we're going to go look up sulfate. Here's sulfate here. We look up barium. And we say, oh, barium is low solubility. Therefore, barium sulfate will be a solid, and we'll write it as BaSO4 solid. Is good? Aluminum hydroxide. We look up hydroxide. Sorry, we'll be done in like 1 minute. We look up hydroxide. We look for aluminum in here and we don't find it. So it would be in all others. So again, it would be low soluble, low solubility. It's going to be a solid. And then the last two examples, I think, are just with chloride. And that's where you've got the copper 1 and the copper 2 that do different things. Okay, so you've got chloride. If we have this copper here, Cl minus, Cl minus, this is Cu2 plus. So that's going to be Cu2 plus. And so it's in all others. If it was copper 1, it would be down below. But what we have is we have copper 2. So it will be soluble. So your homework, 6.3 DCDE, do quote unquote all the exercises, but as always, that might be too much. So just do some of them, do some of each. Okay, you can do the rest of each, you know, over the weekend or whatever, right? Yes. Thank you. Oh. Thank you.